In the previous video, we have seen that maximum likelihood estimation has a simple formulation when the sampling strategy is exogenous. But it has a complex formulation in general. In this video, we investigate another estimator called the conditional maximum likelihood estimation. The maximum likelihood estimation problem consisted in solving this optimization problem. In the previous video, we have derived the contribution of each individual to this quantity. And we have seen that it's too complex, so we want to simplify it. And the idea of the conditional maximum likelihood is to assume that the x's are not drawn, but are given. And we solve the corresponding optimization problem. The conventions are the same, so Sn here represent the event that individual n belongs to the sample. So this is a different estimator. And it has some interesting property because, like the maximum likelihood estimator, it is consistent. It means it is asymptotically unbiased. But, contrarily to the maximum likelihood estimation, it is not efficient. Efficient means that you have the best possible variance among all estimators. So somehow, the precision of the conditional maximum likelihood estimator is less than the maximum likelihood estimator. So this is somehow the price to pay in order to simplify the formulation. We will now proceed as we did in the previous video for the maximum likelihood estimation problem. So we have here the optimization problem to solve, and we will derive the contribution of a given individual to this function. So this is the probability of I given x and Sn, and I will use Bayes' theorem again to write this formulation. So this is the probability of Sn given In xn theta times the probability of In given xn as a function of theta. And as we discussed in the previous video, I have to normalize this quantity to obtain a valid probability function. So this is the sum over all j of the probability of Sn given j and xn theta times the probability of j given xn. As you can see in this case, we don't need to know the distribution of xn in the population. And this is actually convenient because in general, we don't have access to this information. We may know for some variables what is their distribution in the population, like income, age, and so on. But the full distribution of this complex X vector, which contains all the attributes of all the alternatives and all the socioeconomic characteristics of the individual, we have no clue about its distribution. So the advantage, the simplification we have here when we use conditional maximum likelihood is that we don't need to use this quantity. As we did in the previous video, we will look at the two components of the numerator that we also find at the denominator. The first one is the probability of Sn. It means the probability to be in the sample given I and x. And this is what we denoted in the first video on sampling, capital R. Okay, remember capital R is the probability that an individual with configuration In, Xn is selected into the sample. And the second element is simply the choice model. And now if we put everything together, the contribution of individual n to this conditional likelihood function is written as the probability to be in the sample multiplied by the choice model and the normalization over all j of. We have obtained the contribution of individual n to the conditional likelihood function. This is still complicated. In particular, the fact that the probability to be in the sample depends on theta complicates a lot the formulation. But again, there are some specific cases where it will simplify. And this will be when the choice model has a specific specification. And we will investigate two cases. The first one when the choice model is logit, and the second one when the choice model is a MEV model. Let's first assume that the choice model is a logit model. And for the sake of simplification of the presentation, I will assume that the sampling strategy is a pure choice-based sampling strategy. It means that the probability to be in the sample depends only on I, not on X. Actually, there is no real loss of generality here. I could repeat what I'm doing here in each stratum defined on X, and this will apply as well. I'm assuming that the choice model is logit, so in this case, the usual notation for the parameters is beta, beta being the coefficients of the utility function. And to also simplify the notations, the denominator will be denoted capital D. So this is simply the denominator of the logit model. Now I'm looking at the formulation of the conditional maximum likelihood. This is the formulation that we have derived in the previous slide. Let's write this formulation. The first element here, because of our assumption here, is written R in of theta. Here we have a choice model, but the choice model is a logit. So this is given by this formulation here. Therefore, we have e to the vin xn beta divided by d. I will put d here. Okay, so this is the numerator. Then I have the sum over j of r of j xn, which is in our case r of j, and again the choice model for alternative j, which is e to the vj of x n beta divided by d, so I put the d here. And this is when we have the simplification. So we have a d in the numerator and 1 at the denominator, and they cancel out. And now I will make another modification of this formulation. The r, which is in front of the exponential, I will move it up into the v, and of course now it will become a log of r. I will therefore obtain the following formulation: e to the vin xn beta plus log of r in theta divided by the sum over j of e to the vj xn beta plus log of r j theta. And this is interesting because this formulation looks like a logit model. It has the same formulation as the logit, with one important exception. It's like we have shifted the utilities, the v's, by this quantity log of r. Indeed, we see that for each utility, so vi and vj in the denominator, we have a correction factor which is log of the r corresponding to the same utility. Now let's think of the following procedure. Let's say that I just forget about my sampling strategy. I'm using a pure choice-based sample in this case, but let's forget about it, and I will estimate the model like if it was an exogenous sample. So I will apply the formula of the logit. If you look at this equation, it shows that the whole model will be correct. It's a logit model, except for the constants. Each alternative specific constant will actually be biased because we didn't take into account this log of r that is appearing in the conditional maximum likelihood. So it gives us some interesting suggestion for practice. We can estimate the model, ignoring the sampling strategy, and afterwards we can correct the constants using this log of r. So this is what we mentioned here. If the logit model has a full set of constants, the correction for pure choice-based sampling is completely confounded with these constants. And therefore, the practical procedure that I suggested in the previous slide is that one, you estimate the model using the classical exogenous sampling maximum likelihood estimator that we saw in the previous video, meaning that we were using the choice model instead of this contribution of CML of individual n. This provides consistent estimates for all parameters except the constants, because we have ignored this log of r that appears in the formulation. So we have to correct them, and this is the first step. We correct the constants using the estimates of r. And as I said, assuming that it's a pure choice-based sample is not a restriction. So if the sampling strategy is endogenous, you will need a correction term and a constant for each stratum of exogenous variables. Let's have a look at a concrete example. I will use again this simple example where I have two variables. The explanatory variable is travel time, and I have three strata: short travel time, less than 15 minutes, medium travel time between 15 and 30 minutes, and long travel time above 30 minutes. I have three modes of transportations: drive alone, carpooling, and transit. And here is the specification table of the model I plan to estimate. So I have a constant for the drive alternative. I have a constant for the carpooling alternative. Here I have an indicator that says if the travel time is short, which is associated with a parameter here. I have another indicator that says that the travel time is medium, associated with the parameter drive medium. And I have the same two here for the carpooling alternative. I use the transit as a reference. So very simple specification. In the first video about sampling, I have illustrated the various sampling strategies using the same example. And I'm using here the same sampling rates that I've used in that example. Okay, so for simple random strategy, I have the same probability to be selected for all the population, which is 1 over 1,000. It means that I will select 1,000 individuals out of 1 million people in the population. For the exogenous strategy, the sampling rate depends on the value of the exogenous variable, which is travel time. I have short, medium, and long. And for the endogenous, here I have a choice-based sample. The sampling rate depends on the choice that people make: driving, carpooling, and transit. So I have made the following experiment. I have extracted 3 samples, one for each strategy, and then I have blindly estimated the logit model using the sample without caring about anything. These are the results for the simple random sampling. We know that the simple random sampling strategy provides a sample which has the same statistical properties as the population. So we will use this as a reference. Now we have seen in the previous video that when we use the exogenous sampling strategy, we can basically apply the exact same procedure and we will obtain the maximum likelihood estimators of the parameters. And we observed in this case that we get exactly the same results as for the simple random sampling. So this is why I said in the previous video that it is very good news. When we have an exogenous sampling strategy, we just don't need to care about that. We just estimate the model as such. Now let's look at the third strategy, the endogenous sampling strategy, which here is a choice-based, pure choice-based sampling strategy. We observe that all the parameters except the constant are estimated correctly, but the constants are not. Again, if we use the simple random strategy results as a reference, we can see that we obtain something completely different. So what I will do now is to correct. As I mentioned in the previous slide, we just estimate the model without taking care of the sampling strategy. That's what we have done. But now here we have to correct the constants. To do that, we have first to calculate the value of log of r for each alternative. This is what I have done here. I have calculated the log of r for the 3 alternatives based on the sampling rates that are reported above. As you remember, in a logit model, one of the constants must be normalized to 0. So I will do the same for the correction factors. So I need a 0 here. So what I've done, I have increased all these correction factors by 6.90. And this is how I have obtained these values. Okay, this is what I call the shifted correction. So I have added the log of r in all the utility function, and then I have shifted all of them such that the reference constant is 0. I don't want to correct it. And now I simply calculate the value of the constant estimated using the ESS sample, and I just subtract the shifted correction that I have just calculated. And here you see that the values that you obtain by doing so are exactly the same as the values that we have obtained with the simple random sampling strategy. So this example illustrates very well the procedure that I was suggesting previously. If you are using a logit model and you have a choice-based sampling strategy, you first estimate the model, and what you get is a correct value for all the parameters except the constants. So if for some reason you don't need the constants, in particular if you are interested in willingness to pay, value of time, or quantities like this, that's it. You don't even need to worry about the correction. But if you need the constant, for instance, if you want to calculate market shares, then you need to correct them. And to do that, you need to go back to your sampling strategy, remember the sampling rate that you have chosen, take the log, shift it, and subtract it from the utility function. And you get the correct values or the correct estimates of the constant. So this is very elegant. Somehow, so far, I told you, one, we need to use sampling strategies that are different from simple random sampling because they are more practical. But we have to worry about this because in this case, the sample does not have the same properties as the population. And basically, so far, I have shown you that you don't really need to care about this. If the sample is exogenous, use the exact same procedure. That is why it's called the exogenous sampling maximum likelihood estimation, which is the same as the simple random sampling. And I've shown you that if you have a logit model, basically you don't need to worry about it either, even if it is a choice-based sampling. You just need to correct the constants afterwards. Okay, so far so good. Basically, I told you don't have to worry about it, but there is everything else. It means that there are other models than the logit model. What happens in this case? Well, let's look at the MEV model. If you remember, the MEV model has a functional form which is very similar to a logit model. So remember, the idea of the MEV model is that you have a probability generating function. And here I give you the example of the nested logit model, for instance. And based on this probability generating function, you can derive the choice probability provided by the model, which is like a logit-like formulation, where each utility has a correction factor that captures the correlation among alternatives. But there is a major difference here. If you look at the numerator, this term here involves all the utilities of the alternatives in the choice set. While in the previous example with the logit model, it was only about I in the numerator. And same thing at the denominator for each j. Potentially all utilities are involved. Let's see why it's a problem. Because the MEV model has the same form as a logit, I can do the same derivation that I showed you for the logit model with pure choice-based sampling. And this is what I will obtain here, this formulation. But what is the difference? But the difference is that because of what I said before, because of the fact that this term here involves ingredients which are not related with I, well, this correction is not confounded with the constant here, because there is this term here as well, which is in the way. In particular, the VI which is here is influenced by the correction, but the VI which is inside here is not. So this is not as simple as the logit model. We cannot claim that the correction term is confounded with the constant. So it means that we cannot do like I suggested for the logit. Let's estimate the parameters without worrying about the sampling strategy and correct afterwards. But still, it's quite simple. And what we will do is to change a little bit the procedure that I suggested for logit in the following way. We start by including explicitly the estimate of log of R, the correction, in the formulation, like we showed in the previous slide. We put it explicitly in the formulation. So somehow it's about writing a new estimator. And then we can estimate the parameters. So in this case, this is not ESML anymore, right? It's a little bit more complicated, but still sufficiently simple to be applied in practice. And I will leave the technical details out of the way in this video. I refer you to the paper, the references in the appendix, if you want to have more detail. When the sampling strategy is not exogenous, conditional maximum likelihood estimation should be preferred to maximum likelihood estimation. In the case of logit, applying ESML, so exogenous sample maximum likelihood estimation, to the data yields to consistent estimates of all the parameters except the constants. And we have seen how to correct the constants afterwards. In the case of MEV models, ESML does not work. But we have seen that the conditional maximum likelihood is easy to derive. It's a very simple formulation. And in the next video, we will introduce an estimator that should be applied for all the other models that are not included in this list. And we will also summarize the various cases that we have seen.